Alright, here we go with lecture 1.2, and this corresponds to a lot of the material from section 2.3 of the textbook. So for those of you who are wondering about my numerical numbering system, what you'll see on folio is how I'm ordering the lectures, but if you look up here towards the top, I'll try to reference where in the book you could find the corresponding material. So here we're going to be looking at a wide variety of applications, or what many students fondly call word problems. And just a quick warning here, guess and check is not an option. So if you are using guess and check, you will not receive credit on exam. So you need to make sure to show your work, and in many applications that means defining a variable to represent some random phenomenon or some phenomenon in the context of the problem, and then coming up with a equation that models that phenomenon, then manipulating and utilizing that equation to answer the question. So let's look at an example here. So number one, we got a car salesman. He earns 5% commission on sales in addition to $1,000 per month. If his goal is to earn $2,500 each month, how much must he sell to achieve his goal? So my advice when you're working on these word problems is define your variable after the objective. So whenever you're done reading the problem, ask yourself, hey, what's the objective here? Well, the objective is to figure out his sales figure. So that's what I'm going to define my variable to be. So now that I've defined my unknown value after the objective, I'm going to go ahead and try and solve the question. So we need to come up with an equation that models this. So he gets 5% commission on sales. So that means his paycheck means he gets 5% times his sales, so 5% of his sales. That's not the only thing on his paycheck. He also gets an additional $1,000 per month. And that represents his pay. He wants his pay to equal $2,500. So then we go ahead and solve that equation. And really, solving the equation is the easy part. It's coming up with the equation that can be a bit squirrely. So once you solve this equation, all you got to do is subtract 1,000 from both sides and then divide by 0.05. And you get 30,000. So his sales figure needs to reach 30,000 in order for him to get a $2,500 paycheck. Alright, so that brings us to number 2, where we have 3 times the larger of 2 consecutive odd integers is the same as 17 more than 2 times the smaller integer. Find the 2 integers. Now, it's going to be very tempting here to define 2 variables. I recommend against that. You can do that, but here's the catch. If you're going to define 2 variables, you're going to need to define 2 equations. If you define 3 variables, generally speaking, you'll need 3 equations. Define 4 variables, generally speaking, you'll need 4 equations, so on and so on. So when we're talking about multiple equations that share variables, that's a system of equations, which is a bit more complex. So we want to try and solve this with the simplest approach possible. So what you want to do here is try and come up with a single variate equation. So we got 2 unknowns here. So let's let x be the smaller number, because we got a smaller and a larger number. So if x is the smaller number, and we know that these are consecutive odd, then that means the larger number is x plus 2. That's because these 2 numbers are consecutive odd integers. So if you make up some numbers, suppose I have, I don't know, 1 and 3, 5 and 7, 79, 81, 101, 103. Any pair of any pair of consecutive odd integers, you can get from one odd number to the next odd number by adding 2. So if I'm sitting at 79 and I want to figure out, hey, what's the next odd number after 79? You add 2. So all we've done here is abstract that. So our 2 numbers can be represented by x and x plus 2, where x plus 2 represents the larger integer. So now it's just a matter of reading and translating as we go. 3 times the larger, so that's 3 times x plus 2, is the same as, that means equals, 17 more than, so we're adding 17 to 2 times the smaller. And there we are. We just want to go ahead and solve that equation. So again, once you're done, you can solve the equation, and you get x equals 11. So 11 is the smaller one, and we add 2 to that to get the larger, which is 13. So there's our answers, 11 and 13. So here we have a simple interest formula, I equals P R T. This is where I represents interest, P is principal, R is the simple interest rate, and T is time in years. So we're looking at number 3. Sally has the choice of a 4-year car loan. I'm sorry, not a car loan, just a 4-year loan at 7.5% simple interest, or a 5-year simple interest loan at 7% simple interest. If the loan is for $20,000, then which loan requires less interest? So we're basically comparing a 4-year loan versus a 5-year loan. Now, your initial gut feeling might be say, hey, whichever one has the lower rate will be less interest. Well, not quite. You got to keep in mind that 5-year loan is over a longer period of time, which means it will accrue more interest. Maybe, but it's at a lower rate, so it's not obvious. So we got interest equals principal times rate times time. So we know the principal is $20,000. The rate for the 4-year loan is 7.5%, so it's 0.075, and it's for 4 years, and we don't know what the interest is. So we can simply type that into our calculator, and we know for our 4-year loan, that's going to cost or accrue $6,000 in interest. Now let's go ahead and look at the 5-year loan. It's still a $20,000 loan, but it's at a lower interest rate, but it's over 5 years. So if we compute that, we get $7,000. And it becomes quite obvious that actually the 4-year loan is going to be cheaper with respect to interest. Now, monthly payments will be higher, of course, because it's over a smaller period of time. But as you can see, even though it has a higher rate, since it's 1 year less than the other loan, it's actually going to accrue less interest. So that's a simple interest application. Now, this isn't particularly realistic in the real world. Note, compound interest is the realistic model. And we'll look at compound interest later on in the semester. All right, compound interest is an exponential function, so we'll cover that in Unit 4, actually, towards the end of the class. But for now, let's look at some geometry applications. So just some formulas here in case it's been a little while. So area of a rectangle is area equals length times width. Area of a triangle is area equals 1/2 base times height. And if there's one formula students tend to remember from high school, and that would be Pythagorean's theorem, which is a squared plus b squared equals c squared. Now, this is one of the most important formulas in existence, all right, in our perception of the entire universe, believe it or not. And Pythagorean's theorem, this is where A and B are legs of a right triangle, and C is the hypotenuse. So Pythagorean's theorem only applies to right triangles. Now, a right triangle is a triangle with a 90-degree angle somewhere. So here's an example of a right triangle. There's that 90-degree angle. And you have to identify the hypotenuse when you apply Pythagorean's theorem. That's the most common mistake with applications of Pythagorean's theorem is students don't know which side is the hypotenuse. The hypotenuse is always going to be across from the 90-degree angle, and that's what we represent with the letter C. So it's almost like that little 90-degree angle is pointing at the hypotenuse. It doesn't matter how you label the legs. I could call one A and the other B or vice versa. That part doesn't matter. What really matters is getting that hypotenuse correct. So let's go ahead and look at a couple of examples. Nice tip with these geometry applications is draw pictures and diagrams. Very helpful here. So let's look at number 4. We got length of a rectangular picture frame. So I'm going to go ahead and stop there and just draw a rectangle. So we're working with a rectangle here. So the length is 6 inches more than 5 times the width. If perimeter is 156 inches, compute dimensions of the frame. Now, just like I mentioned at the beginning of the lecture, you want to avoid multiple variables. So you want to think about, hey, how can I label all of these dimensions with a single variable? Well, it says right in the very first sentence, length is defined in terms of width. So the length is 5 times the width, so we'll call that 5W. It's 5 times the width plus 6, and the width is the width. So there's our dimensions. So note, it's very important here that we define everything in terms of a single variable. And it says if the perimeter is 156 inches, compute dimensions of the frame. So the perimeter is all the sides added up together. So if we add up all the sides, that's W plus 5W plus 6 plus W plus 5W plus 6. Add all those up and it equals 156. So all I did there was add up all the sides. That's what perimeter is just adding up all the sides. And then we have our equation. We can go ahead and solve that. So we end up with 12W plus 12 equals 156. Therefore, 12W equals 144 and W equals 12. So if W is 12, the length is 5 times that plus 6, which is 66. So it's 12 inches by 66 inches are the dimensions of that frame. So it's like some form of panoramic photo frame. Alright, let's look at number 5. Looking at number 5, a wire is needed to support a vertical pole that is 20 feet tall. The cable will be anchored 15 feet from the base of the pole. How much cable is needed? So we got a pole, and it's vertical in the ground, so we can assume it's at a 90-degree angle. And from the top of that pole into the ground is a cable being staked down. So as you can see, this is an application of Pythagorean's theorem. And it says from the bottom of the pole to where that cable is staked down is 15 feet. We know the height of the pole is 20 feet. And we want to go ahead and compute the length of the cable. So here we can use Pythagorean's theorem since it's a right triangle. Now note, x is our hypotenuse. So it's leg squared plus leg squared equals hypotenuse squared. So that's going to be 20 squared plus 15 squared equals x squared. So that's going to be, let me see here, 400 plus 225 equals x squared. So 625 equals x squared. Go ahead and square root both sides, and you would get plus or minus solving this, because that's an even power equation. Remember we talked about power equations in the last lecture. Is 25. Now, of course, the negative answer doesn't make sense, so the answer is 25 feet. So you would need 25 feet of cable for this application. Alright, let's talk about work sharing a job. So moving on to here, work sharing a job. So this is essentially combining rates. So if we can compute or complete one task per every this many units of time, and one task per every this many units of time, if we add or subtract those, we can get the time it would take if both of those people or machines or operations are working in conjunction. Now you might look at the plus or minus here, which begs the question, well, when do you add, when do you subtract? Use addition if the two forces or two people or two operations, whatever they are in cooperation. Use subtraction if they are opposing forces. And in the case of subtraction, we have to put the dominant force first. Otherwise, you get negative numbers, and you can't have a negative time value. It doesn't make sense here. So, let's go ahead and look at number 6. John can finish a particular task in 7 hours, but when Tom helps, it takes 3 hours. How long would it take Tom to complete the task alone? So you want to identify what you're working with. So this is definitely not one of those geometry problems. You got two people working a job, so I call these the work/sharing a job problem. So whenever you got two machines or people or pipes or what have you working together or working in conjunction, it's essentially a combined rates problem. So we got John. John can do one task in 7 hours. And basically what you got going on over here is we have our individual rates on the left side of the equation, the combined rate on the right side of the equation. So we got to be very careful. That 3 hours, we got to ask ourselves, is that an individual rate or the time it takes together? Well, that's their time when they're working together. So that goes over here. The other individual rate is what we don't know. So it's very, very important. I'll go ahead and add a note here. As you can see in the setup, the individual rates are to the left in the equation above. So we can see for our John and Tom problem here in number 6, the individual rates are to the left, and they got to determine, hey, are they working together or working against each other, or they're working together, so we use addition. So we use addition when the two rates are working together. So this goes back to some problems in worksheet 1. What we want to do is clear the fraction, so we need a common denominator. So we want to get all denominators to look the same. So I have 1 over 7 plus 1 over x equals 1 over 3. So common denominator between 7 and 3 is 21. So I can get this first denominator to 21 by multiplying by 3 over 3 top and bottom. I can get this one to 21 by multiplying by 21 over 21 top and bottom. I can get this to 21 by multiplying top and bottom by 7 over 7. So you got to ask yourselves, hey, are all my denominators the same? Well, not quite. My first denominator is 21. My second denominator is 21x. My third denominator is 21. So two of those denominators are missing an x. So multiply by x over x accordingly. Now that all denominators are identical, multiplication by the least common denominator clears those. So you can cross those out and bring everything down. So that's not 13x. That's 1 times 3 times x, which is 3x plus 21 equals 7x. To go ahead and solve that, you're going to get x equals 21 over 4. In other words, that's 5.25 hours. That's how long it would take Tom by himself. Then ask yourself, hey, does this make sense? Well, we know our answer is going to be bigger than 3 because it takes 3 hours to complete the task when you have two people working on it. Thus, you would assume working alone it would take longer than 3 hours. So this type of application is not very realistic for people because people, when they work together, it's not always perfect in conjunction. But this type of approach is perfect for modeling machines and manufacturing, assuming you can partition the job responsibilities accordingly. So if you can split up the job correctly, then this is a perfect mathematical approach for this. So, this isn't exactly realistic because, John and Tom, they might be friends, and maybe when they work together, they actually work slower because they spend the time gossiping instead of actually working. But if you're talking about like copy machines or manufacturing, this is a good approach. Or in the case of number 7, here's an interesting example. You got a swimming pool with an inlet pipe that fills the pool and an outlet pipe that drains the pool. The inlet pipe takes 3 hours to fill it. The drain pipe takes 12 hours to drain it. And suppose some dingleberry left both of them open. Well, what's going to happen? Well, the pool's going to overfill. Right? If it takes 3 hours to fill and 12 hours to drain, it's filling a lot faster than it's draining. Hence, given enough time, it will overfill. So our test here is one pool, so we can set it up. So we have our two individual pipes on our left with the rate on the right representing both of them working at the same time. And here we are using subtraction because these are opposing forces. All right, we got filling versus draining. They are counteracting each other as they're working. So we use subtraction. Now whenever we use subtraction, we have to be very careful with the order. We got to ask ourselves, okay, which one goes first? Well, the dominant force will go first. So you got to ask yourself, what's dominant here, the filling or the draining? Well, if it takes 3 hours to fill and 12 hours to drain, the filling is dominant. So it's going to work like that, and we don't know how long it takes with both of them open. So be careful here. Big number does not mean dominant. It depends upon the context, right? If it takes me, 10 minutes to run a mile, and you can run a mile in 8 minutes, am I the dominant runner? My number is bigger than your number, that means I'm dominant, right? Well, no. If we're talking about speed and time, it's actually the smaller number that's dominant. So that's why the 3 goes first and then the 12. So we want to go ahead and get a common denominator. Common denominator would be 12x. Let me just go ahead and rewrite this real quick. So this denominator we can get to 12x by multiplying top and bottom by 4x. This we can get to 12x by multiplying top and bottom by x. And here we can multiply top and bottom by 12. So 12x, 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 all denominators are identical. Multiplication by that common denominator clears them. So we're left with 4x minus x equals 12. And therefore x equals 4. So if we leave both the pipes open, it would take 4 hours for the pool to fill up. After 4 hours, it would start overfilling. And that makes sense, right? It takes 3 hours to fill the pool up, but that's assuming the drain is closed. So if you leave the drain open, it's going to take longer to fill up. And that's what we're seeing here. Alright, that brings us on to the next application, uniform motion. We're at the formula D equals RT. That's where D represents distance, R represents speed, T represents time. Now you're going to be presented with a lot of information here. And then oftentimes it's going to be information overload. So what you want to do is organize the data into a chart. And that's what you want to do. So you don't have to follow this strategy, but here's some general guidelines you can. You want to go ahead and set up your chart. Define your variable after the objective. So if I'm trying to figure out a time value, I'll define my variable to represent time. If I'm trying to figure out a speed value, I'll define the variable to represent speed. If I'm trying to determine a distance value, I'll define the variable to represent distance. And what you want to do is go ahead and fill in chart. And when you fill in the chart, this is where you need to listen very, very carefully. One chart will be one column. Go and write that. Will be constants. One column you will define variable. The remaining column, and this is the important part of the problem, we'll use the formula and other two columns. And once you're there, you want to go ahead and use chart to form the equation. Solve, and then summarize as needed. So let's look at problem 8. Two trains leave the same station at the same time going in opposite directions. One train is 17 miles per hour faster. After 4.4 hours, the trains are 506 miles apart. What is the speed of the slower train? So like I said, this can be information overload. So whenever you're presented with a bunch of information, you want to start organizing it. So let's go ahead and start organizing it into a chart here. So I don't know, we'll call them train 1 and train 2. And we got distance that each train has traveled, the speed at which the trains are traveling, and the time. And we want to go ahead and start. We can go ahead and define our variable. So we want to ask ourselves, are we trying to figure out distance, speed, or time? Well, ask, hey, what is the speed? So that's where I'm going to define my variable. All right, X marks the spot. We're trying to figure out speed. Now, if one train is going X miles per hour, the other train is going X plus 17 miles per hour. That's because, it says right there, one train's going 17 miles per hour faster. Alright, so now we want to go ahead and get our constant. So we got one column down, 2 to go. So we need to ask ourselves, do we know the distance that train 1 has traveled? And this is where we normally see, or where I normally see catastrophic errors. If you put the 506 here, you have made a catastrophic mistake. This train has not traveled 506 miles. Train 2 has not traveled 506 miles. The 506 miles is miles apart, and I really stress the word apart. So we don't know the distance that each train has traveled, but we do know train 1 has been traveling for 4.4 hours, and train 2 has been traveling for 4.4 hours. That's because it says right there they left the station at the same time. So they've been traveling for the same amount of time. So this is where we use the formula. So distance equals speed times time. D equals RT. So train 1, its distance that it has traveled is speed times time. So that's 4.4 times x. As we see, speed is x, time is 4.4, so it's 4.4 times x. And train 2, how far has it traveled? Well, it's traveled at a speed of x plus 17 miles per hour for 4.4 hours. Distance traveled equals speed times time. So here it's 4.4 times x plus 17. So this is that key step. So again, we don't know how far each train has traveled. Now it's time to formulate the equation. So we know, let me draw a quick little diagram. If this is my station right here, and one train is going this direction and the other train is going in that direction, and we know that they are 506 miles apart, we need to be able to formulate an equation. Well, if they're 506 miles apart, we know that this train has traveled 4.4x miles. This train has traveled 4.4 times x plus 17 miles. Well, there's our equation. The distance apart is the sum of the two distances. So that's 4.4 times x plus 4.4 times x plus 17 equals 506. And we'll go ahead and solve that. So that's 4.4x plus 4.4x plus 4.4 times 17, which is 74.8 equals 506. So you go ahead and solve that equation and you will get 49. And there's our answer. And that's the speed of the slower train. If I wanted the speed of the faster train, I would add 17 to that. Alright, that's number 8. Let's look at one more uniform motion problem. So here, Rick can run 2 miles per hour faster than Jim. Rick can run 24.5 miles in the same time. Then Jim can run 17.5 miles. How fast can Jim run? So this is clearly a uniform motion application. So we got distance equals speed times time. We got Rick and we got Jim. So let's go ahead and define our variables. It's asking how fast, so we want to know speed and we want to know how fast Jim can run. So we want to figure out Jim's speed. So I'll put x there. Rick can run 2 miles per hour faster, so that's x plus 2. And then we want to ask ourselves, okay, do we know distance or time? Well, it says Rick can run 24.5 miles. That pertains to Rick. So Rick has run 24.5 miles. Jim has run 17.5 miles. So we know how far each runner has traveled. And then we don't know the time, so this is where we use the formula. So we might have to manipulate formulas sometimes. So right now the formula tells us D equals RT. We don't need to know D. We already know the distance value. We need to get time. So we solve for time. So to do that, divide both sides by R. And we know time equals distance divided by speed. Alright, so that means time is distance divided by speed. So for Rick, that's 24.5 divided by x plus 2. For Jim, that's 17.5 divided by x. And we know, it says here, that it's in the same time. Underline that, it's a key phrase, in the same time. So that means those two time values are equal. So we have 24.5 over x plus 2 equals 17.5 over x. We want to go ahead and get a common denominator and solve this. So the hard part's over. Right? Getting the equation is the hard part. Once I have the equation, it's pretty quick to solve. So this denominator is missing an x. This denominator is missing an x plus 2. We got a common denominator. Skadoosh. So we're left with 24.5x equals 17.5 times the quantity x plus 2. And we'll go ahead and solve that. So I trust you can take it over from there. We solve that real quick. That's 17 times 2. And we get 5. And that represents Jim's speed. So that's 5 miles per hour. Alright. And we are off to the last topic, mixture applications. So, mixture applications. We want to go ahead and organize data into chart. And the equation is sum. Alright. So let's look at number 10. A total of $10,000 is invested between two accounts. One is 4% simple interest, the other is 3% simple interest after 2 years. Total interest was $750. So this is using that simple interest formula. And let's just go ahead and call these, I don't know, account A and account B. You can label them as you see fit. And we know principal times rate times time equals interest. We know that from that simple interest formula earlier in this lecture. We know one account is 4%, the other account is 3%, and 2 years has gone by, and our goal is to figure out the principal. Now we know that a total of $10,000 was invested between the two accounts. So we need to come up with a expression representing the principal for account B, assuming X dollars has been invested into account A. So let's just play out hypotheticals. If I put $2,000 in account A, how much is in account B? Well, that would be $8,000. How'd you get that? You subtract. So if there's X dollars in the first account, that means there must be $10,000 minus X dollars in the second account. And then we can run our formula. So interest equals principal times rate times time. So you multiply all those as 0.08 times x. And same thing here, principal times rate times time, that's 0.06 times the quantity, 10,000 minus x. So this represents we got the interest from account A, the interest from account B, and we know that the total interest from both accounts was $750, so there's our equation. Interest from the first account plus interest from the second account equals total interest, which we know to be $750. So you want to go ahead and solve that. So let me go ahead and solve that real quick. That'll be 6 So just solving that real quick. So that's 750 minus 100. There we are. So we get x is 7,500. So that tells us we got 7,500 in the account with X, which is account A, so that's in the 4% account, which must mean we have 2,500 in the 3% account. And there's our answer. Alright, let's go ahead and look at one last example. So in a chemistry class, 12 liters of a 14% alcohol solution must be mixed with a 20% solution to get a 16% solution. How many liters of the 20% do you need? So I used to work in a chemistry stock room and I did stuff like this all the time. So we basically got solution 1, chemical solution 2, and mix. We got an amount for each. We know its strength. And if we know the amount and the concentration, we can use those together to compute the amount of, was it acid? No, alcohol in this case. Right. You know, if I have a gallon of an alcoholic solution that's 50% alcohol, then I know I have half a gallon of pure alcohol in there, just by multiplying accordingly. Alright, so we are mixing a 14% solution with a 20% solution to get a 16% solution. So it's very important that you get these percentages correct. If you get them wrong, then it'll throw everything off. So you got to ask yourself, hey, is this even physically possible? Well, if I mix a 14% solution with a 20% solution, I'm going to get something that's stronger than the 14% but weaker than the 20%. So you're going to get something in between the two. Now, if I use mostly 14% solution, then the concentration will be closer to 14%. If I use mostly 20% solution, then the concentration will be closer to 20%, but it's going to be somewhere in between. The analogy I use, as disgusting as it is, if I mix beer and whiskey together, you get something stronger than beer, but weaker than whiskey. You get something in between the two. That's kind of what we got going on here. So we got 12 liters of the 14% solution. Must be mixed with a 20% solution. How many liters are the 20%? That's our goal. We want to figure that out. X marks the spot. And we're pouring solution 1 into solution 2 to get the mix. So we're dumping these two things together. So that means the amount of the mix is 12 plus X. So we're assuming no chemical reaction is taking place. And we can compute the amount of alcohol. So I have 12 liters of a 14% solution. That means 14% of the 12 liters is going to be pure alcohol. So in other words, in solution 1, we got 1.68 liters of pure alcohol. Here it's 20% times X. Here it's 16% of 12 plus X. And we can use conservation laws to derive our equation. So the amount of alcohol from the first solution plus the amount of alcohol in the second solution equals the amount of alcohol in the combined solutions. So keep in mind we're mixing solution 1 and solution 2. So if I pour these two together, then the amount of alcohol in each ingredient equals the amount of alcohol in the mixed solution. So in other words, 1.68 plus 0.2x equals 0.16 times 12 plus x. And we'll go ahead and solve this. That's 1.68 plus 0.2x equals, let's see here, 16 times 12 is 192, so that's 1.92 plus 0.16x. So getting our x's on one side, that's 0.04x equals 1.92 minus 1.68, 0.24. Therefore, x equals 6. So, there's our answer, 6 liters. So, if we want to end up with a 16% alcohol solution, we're going to have to pour 6 liters of a 20% solution into 12 liters of our 14% solution. That will give us 18 liters of a 16% solution. And that's a wrap. So guys, just a heads up, I've covered most of what's on worksheet 2, but not all of it. So worksheet 2 is a bit longer than worksheet 1, so I do not recommend procrastinating on it. So I recommend you get started on the word problems in worksheet 2, and the rest of the material in worksheet 2 I will be covering in the week 2 module. But keep up the hard work and have an excellent day.